All right. So the first derivative is telling us about increasing, decreasing. What does the second derivative tell us about the shape of a curve? It tells us concavity. All right. So f double prime tells concavity. If f double prime of x is positive, then what? Concave up. And if f double prime of x is negative, then concave down. Okay. So again, we're interested in when is this function positive, when is this function negative, just the same as we were with f prime. Right? We started off by saying, like, when is it 0? And then in order to kind of determine the shape of things, we kind of looked at when is it positive, when is it negative, right? And so we'll do the same type of thing with f double prime. When is it 0? When is it undefined? And then we'll use those intervals in order to determine when it's positive and when it's negative. So let's do that. Let's say we were looking at a function. And let's look at x cubed plus x. Let's look at something simple, just to kind of get a sense of what's going on. And I would like to know when f is concave up and when f is concave down. So I need to find out when its second derivative is positive and when its second derivative is negative. What is the second derivative? F prime is 3x squared plus 1. F double prime is 6x. So what are the important times for f double prime if I'm trying to figure out when it's positive or negative?
When x is positive or x is negative.
Yeah, and why those windows?
That gives you when you multiply that, it gives you either a positive or negative. If it's positive, it's concave up. If it's negative, it's concave down.
Yeah. Inherently, what I'm doing here is I'm trying to find out, like, when is it 0 or not exist, and in that case, it's 0 when x is 0. So that's going to be a dividing line. And 6x will always exist, so I don't have to worry about these times. So I have a number line, an f double prime number line, and it's broken up into intervals. Intervals where it's positive, intervals where it's negative, intervals where it might be neither. But there will be kind of division lines on that interval. And those division lines will correspond to these times when it's 0 or doesn't exist. Because if you move from positive to negative or vice versa, you either have to travel through 0 or you have to jump. And if we're talking about continuous functions, they don't jump that often unless there's a does not exist in there. So there's going to be a big division at 0. So I'm going to put that critical value on there. Here's a time when the second derivative is 0. So what about over here?
That's all negative, anything less than 0.
Yeah, so I'm going to take a test point. F double prime of, say, -1 is -6. Right? Or I could just look at the function and try to decide what's happening over here. And the second derivative is always negative over here. And then I'll take a test point from over here. F double prime of +1 is 6. That's telling me that f double prime is always positive over here. So when is f concave up?
Greater than 0.
Yeah, here when it's plus, 0 to infinity. When is it concave down? Yeah, this other interval, -infinity to 0. So it looks like the concavity changes at 0. It was concave down, now it's concave up. So we have a special name for these times. We call these inflection points.
And what happens when it's 0?
If the second derivative is 0, it's whatever, right? That will often correspond to a time when the inflection changes, but it may not. If the inflection does not change, then there's no name for it. But in order to change from negative to positive or positive to negative, it'll have to be 0 in between. That or there'll have to be a does not exist there. Because there'll have to be some type of discontinuity. So yeah, these times when the second derivative changes sign are inflection points. So it's concave down over here, and it's concave up over here. What about increasing, decreasing? I know that it's concave up when x is positive, and I know that it's concave down when x is negative, but what about increasing, decreasing? What would I do? I'm going to look at the first derivative, and what am I going to do with it? Find out when it's 0, or when it does not exist. And it will always exist, so I don't have to worry about that. There's not any division by 0 happening here. Nothing strange. I just have to solve this equation. So 3x squared is negative 1, which means that x squared is negative 1/3, which means that x is positive or negative square root of negative 1/3. Is that a real number? No, right? Square root of a negative number does not exist. No solutions. So what does our number line look like? Nothing. Yeah. So there aren't any divisions. All of the candy's the same. I don't have multiple bowls of candy. I just have to decide whether this is always increasing or always decreasing. Which is it? How do I know? I can figure it all out from the first derivative, right? The first derivative is telling me increasing, decreasing.
Just plug in a number.
Yeah, take a number, right? How do I know what candy's in the bowl? Grab your favorite piece and taste it.
Just like plug in 2 or something.
Sure. So I'll take 2. F prime of 2 is 3 times 4 plus 1, right? 3x squared plus 1. So that's 13. Do I care that it's 13? No, I just care that it's positive. So what's that telling me? What's that telling me about F? Always increasing. F is always increasing. F is concave up, 0 to infinity. F is concave down, negative infinity to 0. F has an inflection point when x equals 0. Does F have any maximums, minimums? Are there any extrema on F? No, why not?
No solutions.
Yeah, there weren't any times when the derivative was 0 or did not exist, right? This function is always increasing. Right? Extrema happen when there's a change in direction. And here it's always the same direction. Inflection point seems like a good point. So what's the y value? If x is 0, what's the y value for the function? The function is this one, x cubed plus x. So where we are is this guy. So f of 0 is 0 cubed plus 0, which is 0. Here we are. So there's a point 0, 0. That's one point that's on the graph that I know. I'm going to take all of this mess and I'm going to try to draw a picture.
Does inflection and expansion change red?
An inflection point means that the concavity changes at that time. So it stops being concave one direction and starts being concave another direction. It means that the second derivative has changed signs. It's an interesting time, and so I want to make sure that it's on my graph exactly. It's an important point. So here it is, 0, 0. And I know what? That the function is always increasing. So here it is, always getting bigger. And I know that between negative infinity and 0 on this window, negative infinity to 0, it's concave down. And it's increasing. So it's going to kind of be bendy like this. Right? Concave down, but increasing. And then after 0, it's still increasing, but it's concave up. So it's going to be bendy like this. So there is a rough sketch of what f of x looks like. Yeah? So I don't need a graphing calculator. I don't need software of any kind. Right? I can get a shape of what f of x looks like just based on its derivatives. Questions here? That's like half of 4, 3, and 4, 5. It's all of 4, 3 and half of 4, 5. Okay. Chapter 4, like it's just these little tidbits that kind of expand stuff that we already know. It's adding algebra to these kind of conceptual questions that we brought up in chapter 2 and 3.